Greetings, everybody. Good to see you here. Hi, Fan. We made it here this time. I'm feeling punchy. I must be feeling punchy today, I guess. I'm not sure. No comments for the good of the order. I did notice in looking at the previous recordings for these classes this week, so 6.1 and 6.2, that they did have nice long introductions of places, of geothermal reservoirs around the world. Schwarzgeni in Iceland particularly starred, I think, on today's one in 2022 or 2021. I can't remember which one. Anyway. So I haven't done so much of that. I don't think you need so much mental health help now that we're way out of COVID. I think people were a bit gentle or more tender in those days and could use it. So that's why we did that. We'll carry on talking today about geochemistry. Remember last time, if we zip back, we made the case that this is our all-important relationship that we have to deal with. We only make geothermal energy when all of these things are up, and two of them are under our control largely. If you use CO2, I guess it has a different specific heat capacity. Mass flow rates by getting lots of water through in highly permeable connections. High temperatures by getting water through in tortuous connections which have large heat surface area, as we've talked about. And those can be influenced by mechanical changes, thermomechanical changes, contraction and of matrix blocks, and dilation of fractures as a result of that, but also due to chemistry effects. So we talk about chemistry of reservoirs, the concentrations are typically high. We can look at understanding how dissolution and precipitation proceeds within reservoirs, whether they're retrograde or prograde reactions, and we can say something about the rates at which those occur, in addition to being able to define the equilibrium characteristics. And we talked about looking at how these reservoirs are interactive in terms of processes, in terms of the physical flow condition, the chemical transport condition, and also temperature transport in those reservoirs. We represented it in the concept of these kind of longitudinal sections from injector to recovery well. We made the case that depending on the temperatures, we net dissolve material such as silica as the temperatures get hotter as we go through the reservoir, or precipitate retrograde minerals such as calcium carbonate as we go through. These would expect to have some influence on permeability, and of course in affecting permeability, so maybe silica is not so important because we saw last time that the concentrations at equilibrium are quite low for silica. Actually, they're similar to the temperatures we were looking at. But if you looked at this and you look at deposition of calcite, you'd expect to see that reflected in a signal on the flow system. And if we're precipitating at outlet, for instance, we'd expect the influence of that to look like this. Pressure changes across the reservoir would be altered, because if we have the permeability go down here, we have to have higher pressure gradients to drive fluid across the reservoir at the same velocity, because we have continuity if you just think of this as a one-dimensional flow within a tube. And so this interaction is kind of important to us. There are very complex models to look at that. This isn't a modeling class. There's certainly, you can find stuff online to be able to get insight into that. But we did make the connection last time that in terms of these three fields, flow behavior, transport of dissolved components, and transport of heat, we can define those by conservation equations that say the transport of some quantity, be it pressure, concentration, or thermal energy, conforms to mass quanta of that in versus quanta out, and what doesn't balance ends up being an accumulation of that property. And so the dependent variables we'd have for the flow system would be in terms of pressure and volumetric flow rate. The The components in terms of mass solute would be concentration of that solute and mass flow rate of that. Mass flow rate of the solute carried in water with advective and diffusive fluxes. And if we're looking at solving for the heat flow within the fluid and the reservoir, then the conserved quantity would be temperature and a heat flux. What we've called it H dot, would be the equivalent of our heat flux. And so we can use these conservation expressions quite straightforwardly by substituting in for the conserved quantities, density in this particular case, well, this conserved quantity, and be able to write an individual PDEs that represent these systems. So one of these is for solute flow. We won't treat it in great detail, but we realize that each of these expressions are actually rather similar. They have an accumulation term, which says how pressure, fluid mass, or dissolved mass, or thermal energy accumulate. We have a term that represents how it's carried by advection in the bulk motion of the fluid. It doesn't exist in the fluid flow equation, but it does for convective heat transport and convective mass transport. And also it can diffuse according to Fick's law, Darcy's law, or Fourier's law, which means that pressure, temperature, or concentration get driven by the gradients of those in space, dt, dx, and through a coefficient, in this case defined in terms of thermal conductivity. All by way of saying that all of these expressions look the same, and that the one that we would be interested in for mass transport would look like this, would be these components. Accumulation of dissolved mass within the water in an element, the mass transport of that by advection, and the mass transport of that by diffusion. And all by way of saying, if we go back to this is exactly that expression. So I'm not going to belabor this point, but if we're looking at fluids, dissolved components being carried down gradient or downstream, we can make that calculation just by solving a PDE like this. And in this, we have accumulation, we have a mass transport by advection, and we have mass transport by diffusion. If I write it differently, it's just dc dt equals d minus advective velocity times concentration gradient in space plus diffusion coefficient times the second order dx squared. So this is how we've seen it before. This is how it's written here, and written just by taking parameters onto the left-hand side and leaving this reaction rate term here. So this is just the same as this. It has to be in the same units as rate of change of concentration, mass per unit volume per unit time. And so you could think of this as an input of chemical species within the bucket according to these units that occurs either by adding it or as a transformation between chemicals which are already present within the water within the system. So if we have reactants A and B that turn into product C, they're related by this stoichiometric expression that defines behaviors we talked last time. When the behavior is at equilibrium, the forward rate is of producing C from A and B versus the reverse rate of producing A and B from C is in equilibrium, so this can be equated to each other. We can write them as defined in terms of these rate coefficients K1 and K2, and as a result we can define a reaction rate coefficient, which is this. We called this, we used a log, last time we called it log K for this solubility control. And we can define that in terms of these. If the stoichiometry of this is 1 mole of this plus 1 mole of this equals 1 mole of the compound C, then we can define this in terms of what concentrations of these in terms of moles we need or we'll get when we're in equilibrium. And so we can write that in terms of these reaction coefficients. We can take we can just divide one side by the other. And if we do that, and if we know the magnitudes of these rate constants here, we can, which are 10 and 1 here, we can write this in terms of the molar concentration of C, which is X, and the amount, if we only have a single mole within the system, then we know by definition the concentration of A and B have to be 1 minus this concentration. So we can write this in terms of 1 minus X for A, 1 minus X for B, all squared over the concentration of X, and it has to conform to this. If you solve for this, you find out that the concentration of C has to be a bit less than a tenth, and the concentrations each of A and B is 0.9. So we can get the equilibrium behavior from this. But also, we can define relative to these reaction rate coefficients, defining the forward and reverse rates of reaction, we can use this to define this rate coefficient. And this rate coefficient is exactly what this source term is, by which we're adding the rate at which we're adding A and B or C to the system is defined by this. And so this is another accumulation term, or transformation term if you like. And so if we wanted to solve this system for 3 compounds present in water and flowing from upstream to downstream, the way to solve it would be to write this conservation equation for 3 species. We'd write it for species 1, I guess for A, for B, and for C, or for their concentrations. So we'd have 3 equations. And for each of these 3 equations, we'd have values for these reaction coefficients, which are really the ratios of K1 and K2, but just defined in terms of what the actual concentrations of those are in the fluid at that particular time. So these concentrations define how quickly they will transform, so how quickly A will be produced, and that will go in this first equation. So to be able to solve for 3 species going through from upstream to downstream, we'd write a PDE all the way through from upstream to downstream for each of those 3 compounds, components. And by adding these reaction terms onto the back side, we'd be able to get this transformation as we go from upstream to downstream. We'd be able to predict exactly what this response was in terms of silica and also in terms of calcite, based on how temperatures would change along the system and also how concentrations of the different compounds would change along the system. The other thing that we could also rate, not important for us really, because it's very small in comparison to the heat that we already have in the reservoir. Also with these reactions, they may be exothermic or endothermic. They may create heat energy or they may consume it in allowing the reaction to occur. And that can be defined in terms of the heats of reaction, which are defined for individual reactions, but the product of the heat of reaction, which is a physical parameter for any particular reaction, and the rate at which is progressing in terms of this rate, which is a function of the relative concentrations at any moment in time and position within the reservoir, every little box or element within the reservoir, we can add that into the heat flow equation in that we add heat or subtract heat from the reaction due to the reaction, and we can take a balance of that as we transit through the fluids in the reservoir. So this is not to get the behavior of heat within the reservoir, but it's to allow for fluid flow, maybe starting at isothermal conditions, to be able to define exactly what the temperature distribution would be in the reservoir as a function of heat input. And of course, if we're working in a reservoir which has already got cold water flowing through a hot reservoir, this would also describe that behavior. Turns out that these heats of reaction are going to be trivial in that particular system. And so, all by means of saying that I had my pen on the pad, it doesn't allow me to move. All by way of saying, if we have a complex relationship, we have multiple fields operating that interact with each other. We have concentrations changing permeability. Permeability will change the pressure distribution through the reservoir and change the rates of flow overall to the effluent well. We have temperature changing in the reservoir, which will affect the outlet temperatures. This will be also influenced by the changes in flow rates for the system. High flow rates will, as we know, changes the pattern of how we draw down heat within the reservoir and deliver heat to the exterior recovery well. So it turns out that understanding these behaviors is a critical part of geothermal energy. So it's not a modeling class, but perhaps you can get at least a flavor for the fact that if we want, I'm not going to go through this material, it turns out that the things we do in modeling these systems in reservoirs isn't so different from what we would do within a contaminated aquifer. But since we know that pressure drives flow within our reservoir due to Darcy's law, that heat flow within our reservoir is controlled by Fourier's law and the conservation equation, then we can write the equations. In this case, we've most recently written the one for concentration like this. This is exactly what we've seen. We have an accumulation term, we have a transport term, mass in, dissolved mass, in versus dissolved mass out of the bucket, where we divide the aquifer into a series of elements by diffusion and by advective behavior. We have a reaction rate term, which we just talked about, which is an input flux term, which we could think of it. And so what we can do is we can write this equation as something that looks like a matrix equation that would be A times dc dt plus B plus C. I think I did this here, right? And just made the fact that these coefficients act on the advection term, diffusion term, and the accumulation term. I'm not doing anything different from that. But importantly, these would be matrices which would operate, let's call this D instead of C, and this is equal to Q. And so what we could think about is that this is a matrix that operates on all the magnitudes of concentration changes in time at every single location in the system. So we look at this upstream to downstream system. We look at defining individual elements which fluid flows between. Each of these elements have an individual nodes in them and concentrations from upstream 2, 3, 4, 5, 6, 7. So all the concentrations for each one of these nodes are included in some kind of vector. And so if we look at this, we can divide this into terms which operate on the concentration. And so these must include these spatial gradient terms, dx and dx squared, or d dx and d dx squared, and some that operate on these rates of change terms. No spatial component here, only a change in time. And so if we divide this up, we could put this equation together by writing this as, for this equation here, this is controlled by advection. So this term here would be this. So this multiplied by concentration would be this term. But the reason that it's entered here is that this term is a function of the advective velocity. And the advective velocity is a function of pressure through Darcy's law. And so this term would go here. So in our particular component here, that would be this. This would be D. The one that acts merely on concentration would be this term here, which we've called B. Be a matrix. And the one which operates on as accumulation would be this term here, which we've called A in this. So all by way of saying, we can take this equation and write it just as a single equation also. This is just one equation, but it includes a matrix, which is if we have 7 concentration magnitudes, this would be a 7 by 7 matrix. This would be a 7 by 1 vector. This would be a 7 by 1 vector. This would be a 7 by 7 matrix. This would be 7 by 1. So in other words, it would look something like this. Seven by 7. All functions of the properties of the aquifer, and 7 by 1. C1 through C7. And so we can do that for concentration behavior, the mass transport. We have a similar relationship to this for the thermal behavior. So this would be A T dot plus B plus D T equals this. So these would be new different matrices. These would be vectors just like the concentration. And so these would operate here. This would be this is the one that's operating on diffusion. So this would be B. This would be D, because the advective flux that's driving this would be driving the temperature. This is defined by the advective flux, which is defined by Darcy's law. So it has to operate. This times this would be part of that equation. And the accumulation term would be A. This would be for temperature. This would be for concentrations. This would be for temperature. This would be for temperature. And if we did the same for the flow equation, we'd end up with a term in here, which would be B for fluid flow. This would be A, which would be our storage term for fluid. And the only point I want to make is that since we're interested in the interaction of these fields, how the pressure influences closure of fractures, how changes in the temperature allows fractures to open and changes the permeabilities, which would go into this term here. This would be changing permeabilities. Then we can get the interaction of these by solving a very complex suite of equations which allows the interaction of these. Importantly, if we ignore the advective term, then importantly, if this is going to do it for me, does it? Should be blunt. If we forget the advective term, the only terms we'd have within this matrix would be the terms on the diagonal here and the terms on the diagonal here. So this means that fluid flow and heat flow and mass transport of dissolved components all occur in isolation because they're not linked to each other in any way. There's no feedback within the system because the flow behavior is defined by Darcy's law and accumulation of fluid mass. Heat transport is defined in terms of Fourier's law for diffusion, conduction of heat in solids, and accumulation. And mass transport is just by diffusion and accumulation, no advection. It's only when you start putting in the terms that represent advection do you start populating the off-diagonal terms. And so these off-diagonal terms are basically the feedbacks between these individual fields, whereby you can change fluid pressures, which will change displacements by opening fractures by the fluid pressures. Those displacements will change permeabilities, and those permeabilities will change rates of flow and transport by advection, which will in turn change the temperature distribution from just diffusion and the mass concentration from just diffusive mass transfer. So the bottom line is no more to say than this, is that individually each one of these lines represents either the flow equation, the heat flow equation, or the mass transport equation. When it only has terms on the diagonals, they're completely independent of each other. They can operate without any knowledge of what's going on in the other field. As soon as you add advection into the system, then that's another feedback. But also you can have other feedbacks that will populate the other off-diagonal terms. So it becomes very complex at some stage. We haven't and we won't talk about displacements in this class, but clearly if you cool down an aquifer, as we know, the matrix blocks contract, the fractures expand, and there's a feedback as a result of that as well. And so we could also incorporate that if we wanted to. So that's all I want to say. So way beyond this class, well, it's not part of this class, but it's worthwhile painting the big picture. Some information on how you can solve those things. There's a whole course online if you look on my website on how to do that. And I just thought I'd finish off today by looking back at some of these things, only in a very specific component. The talk last Friday by, was it Hui Wu or Wu Hui, I forget which, was talking about these interactions, both mechanical, thermomechanical, fractures getting larger or smaller due to heat, chemical dissolution, either for prograde in dissolution or by precipitation, and also pressure solution was one of the things. And so the interest in this is exactly what these interactions bring in terms of changes in these systems. So this isn't particularly new. This is more than 20 years old now. I can remember presenting this at a meeting in Stockholm in 2003, among other places. And so just making the case that these kinds of behaviors are important in lots of situations. This is a picture of the geysers, 170 kilometers northeast of San Francisco, near Napa Valley. A conventional hydrothermal reservoir with all the things going on that we've been talking about. This is the schematic for Yucca Mountain, the drift heater, the large-scale drift heater test. It comprised a single drift off an adit off a main drift, an observation drift. And in this drift were a whole bunch of railroad, those black tanker railroad cars you see carrying oil on the railroad, cars which were heaters in this to represent, were surrogates for heated radioactive waste canisters placed underground. And it was to understand the behavior around this drift as a function of the heating of the drift. So kind of a reverse geothermal problem. Starts off cold, gets heated. As the heaters bring it up to 80 degrees centigrade or so, these partially saturated volcanic rocks here lose all of their moisture as it evaporates and collects above them where it condenses. And all of these fans are fans of monitoring instrumentation. So instrumentation to measure changes in electrical resistivity, to do tomography between the upper and the lower fans of boreholes, to measure changes of electrical resistivity as a proxy for saturation. They had seismometers in them, they had thermistors in them, and these red components here were actually wing heaters. And so the idea is that the drift would contain the canisters, but next door to the drift would be another drift with canisters in it as well, and these might be on 50-meter centers for a whole repository. So to get some of the effect of these adjacent boreholes or drifts warming it up, these were also heaters that were present to actually bring up the temperature of the... And it was turned on in December 1998. I remember I was there a couple of days after it was turned on. And this may not be Slipner. Slipner is a famous CO2 sequestration site where they are injecting CO2 in the North Sea off the Norwegian coast as part of a requirement that when they bring gas out, it comes up rich in CO2, and they're required by Norwegian law to re-inject the CO2 into a lower reservoir on the seabed. And so these things that we're talking about, and I can't change the size of this now, don't know why. Okay. So these THMC processes, so they're often referred to as THMC, thermal, hydromechanical, chemical processes. The fields themselves can operate on their own, as we just talked about, without any interaction. But as soon as you add convection into the system, convective transport of heat, convective transport of dissolved mass, then all of a sudden they're linked. And once you add mechanical behavior, these systems are very strongly mechanically linked, primarily because permeability is a function of aperture cubed. So a small change in aperture will make a big change in permeability. Fractures are the softest part of the system. The matrix blocks are very rigid, the fractures are very soft. So if there's any stress change, almost all of that stress change will be manifest on these blocks, which are on the fractures, which are very soft. So the fractures have a stiffness like a spring. The blocks have a stiffness also. This stiffness, not permeability, is very high. This stiffness is very low. And so if you get a change in stress, almost all of it will be visited on the aperture of the fracture, which is this. So they're incredibly sensitive to changes in aperture. And so understanding something that happens within these flow fields is of interest. So lots of complex models to look at this that involve linking thermal hydromechanical processes when you get changes in temperature, how it affects permeability and affects flow, and also it affects the heat, affects the mechanical deformation through the stiffnesses, and is manifest on the permeability field and affects transmission through the system. And so big experiments like this and the FORGE project, which we haven't talked about, are demonstration projects to be able to look at field scale how these complex interacting processes interact to physically say whether they increase permeability or decrease permeability, where they increase permeability, how long they increase permeability for, and to be able to define what exactly those impacts are on the full system. So that was done for, in this particular test, 4 years of heating, 4 years of cooling. The temperature fields around the drift were monitored with these boreholes, and also measured changes in the emissions of CO2 were evaluated in this as well. And so these are just some experiments that we ran to be able to look at those complex processes. And to make the cases, sometimes all is not what you expect. And so the materials that were used were novaculite. Novaculite is basically 100% quartz. And so this would be prograde. As you increase temperature, it will preferentially dissolve the material and put it in solution. And limestone, which is the opposite, retrograde. As temperature gets warmer, it becomes less soluble and deposits. And so I'm not sure that we thought that at the time, but we did that primarily on the vaculite, the ones we'll look at. They behave rather differently. The reason for choosing quartz, rich rock, is that when you net dissolve material, you don't change pH. So you don't have to worry about that in trying to analyze results. And so these are a bunch of experiments that were done on core. The idea is that if you flow from one end of the core to the other, you can get under a pressure gradient a measurement of the fluid that comes out of the fracture in this core. You can measure the mass dissolved in the components that come out of the fracture to get a mass balance on what's dissolved from the system. And you can also look at the changes in porosity by doing X-ray CT if the resolution of this is high enough to be able to see what's going on. So these are just experiments that were done here. They were done in the CQI, as it was called then. I think it still is called the Center for Quantitative Imaging. This is a chalk core, not an evacuolite core in our case. These are flow rates in, flow distributors in. So this is plumbing to get water out, plumbing to get water in. In this is 3 individual tubes to be able to do 3-phase experiments, 3 different fluids, although we just used 1. A sample that goes in the middle, a latex sheath which covers the whole thing, so that you can put it into this core holder, apply a fluid pressure onto this sheath within the core holder, confining pressure, and of course this sample is already present inside this sheath, which is then present within inside the core holder. Ends of the core holder are sealed, so you can pressurize this and apply this pressure, and end-to-end flow from one end to the other. We wanted to do the experiments at temperature while flowing inside a transmitter to a receptor, a CCD camera with a radioactive source here for X-rays. This is the core holder in a chuck, just like you'd see on a lathe, which is turned through 360, then back through 360, just to be able to scan as this is moved up and down through the stage, so that you can individually take multiple slices of this as this indeed turns backwards and forwards as it rotates. And so you don't usually do that to a patient in the hospital. You lie on a bed in a CAT scan and it rotates around you. But here it's more convenient and actually with better resolution if the X-ray is fixed and the sample moves both up and down and around within the scanner. Flow rates in here, this is coiled tubing so that you can turn it through 360 degrees and then back again. You don't keep on turning it like a screw, you turn it backwards and forwards. And since we wanted to do these heat experiments at temperature, we just wrap this in heater tape. So this is just heater tape, a resistance heater that will bring up the heat, and actually it was then had a sheathing of the insulation that you see put around pipes to be able to hold the temperature in. So this is basically the idea. You have a pressure in, you have a pressure out, you measure the pressure drop across the sample with a differential pressure transducer, you apply a confining pressure on the interior of the sample has a fracture along the length of it, which water will flow along. You collect the fluids at the outlet, you measure concentrations to get an assay on the mass that comes out, you try and get changes in porosity from the X-ray CT, and you can use Darcy's law to calculate what permeability is from looking at measuring the volumetric flow rate as a function of a known pressure gradient you apply across the sample. That's a sample. It came from Arkansas, as I recall. It wasn't Arkansas in evacuolite. Had a break in it, had some staining. It was a natural fracture. It was drilled along the axis of the originally present fracture. And this is the response. The reason always to do experiments. So what you could do is, if you have Darcy's law, I guess this would be an area. If you apply a pressure gradient from end to end over a given length, you measure the flow rate, you can calculate permeability. If you know permeability, you can calculate equivalent aperture, which is what's shown here. And so this is a proxy from permeability. You could just as easily have plotted permeability, I guess. So it starts off at a quite tight, 12 micron fracture, very tight. And as the only thing that's done to this is the temperature is increased. And as the temperature is increased, the dissolution of silica out of the system rises. So there's a finite dissolution of silica. So this references this side here. And as you increase the temperature, you measure a change in permeability in the system. So this is the curious thing. Again, the reason for doing experiments. Why, if you're net dissolving material from the porosity, does the permeability go down if the porosity should be increasing if you're net dissolving material from that? And when you take it up from 80 degrees to 120 degrees, again, we're net dissolving material. We don't have readings for these dissolved components, but you get this behavior where the permeability goes down again. Then when you take it up to 150 degrees, obviously the pressures in here are bigger than atmospheric because it doesn't boil. And again, the permeability goes down. So your net dissolving material, you should be net increasing permeability. And we also know that, porosity. We know that porosity is equal to aperture divided by spacing. If you net dissolve and net increase permeability, you'd think that you'd net increase permeability. Doesn't happen. So something else is going on. So what you could do is you could look at calculating how much material is dissolved. And so, in other words, you could look at if you have a fracture and it changes aperture. And so if for some reason the aperture changes and it's being reduced and it changes by some amount, delta B, and this occurs in some small time step. So you can calculate what the delta B dt is, because you can get this from permeability, right? You can calculate directly from changes in permeability. But also, you'd expect that this dB dt, if you multiply this aperture change by the density of the dissolved mineral, so if this is being, I guess, dissolved, I suppose if it's being dissolved, you'd expect it to go the other way. If this is mineral material that's being removed, then the mass of that mineral would give you, if you sum it up over the whole fracture, a mass concentration that comes out of the fracture. So the idea is that if you measure both the dissolved mass concentration coming out and the volumetric flow rate, Q flow coming out, this gives you an idea of the change in aperture through the mass balance in the fracture of the dissolved mineral, and this gives you something about the fracture measured from the flow field. And so you can look at comparing these. So we can definitely measure this in the effluent fluid. We can definitely calculate what this is by measuring the change in permeability as a function of time or aperture. And we can compare the two as an aperture rate. We can look at models which would describe exactly what's going on. And if these measured rates of dissolved mass coming out of it can be correlated with what we'd expect to happen from some kind of model of what's going on, then if we can get congruence between our model and the actual measurements, we have a chance of being able to limit exactly what's going on. Of course, if the fracture permeability is going down with time, it suggests that we're net dissolving material, but for some reason the fracture is growing. So the observational data suggests that if permeability is going down with time, we're net precipitating stuff, and therefore we're occluding the fracture. But that's not what we see. We're net dissolving material and getting this result as a function of that. And so the suggestion is that what we're getting acting in this system is pressure solution. So the idea of pressure solution is that if you have a fracture which would look like this is an idealized part of it. If you take the asperity contacts and isolate exactly what they are, like this, so that a portion of the fracture is in contact, this is in contact, then it turns out that if you have stress applied on this, then that has to be transmitted only across this solid component here. So the stress will build on this contact. There is no stress on this contact here. And if you apply a stress to a mineral, then that mineral will dissolve more rapidly than if it's unstressed. So pressure solution is exactly that. It's the propensity for a mineral to dissolve under stress, preferentially faster than it would do on a free face. So the mere fact that we're dissolving, net dissolving materials and the aperture is going down suggests that the material is coming from this contact by pressure solution, and that's the mechanism that's going on. So you can measure the concentrations dissolved in water. You can measure the permeability change and correlate those. The other hope would be that you could measure the porosity changes in situ by using X-ray CT. That's often possible in porous media because the pores are big in relation to the resolution of the CAT scan. And in fact, the resolution of the CAT scan is usually defined as a function of the sample size. It's usually a 1,000th or a 2,000th of the sample size, because that's the size of the screen that collects the ray from the source through the sample and then onto this raster on the CCD screen. And so the resolution is usually 1,000th or a 2,000th of the diameter of the sample. And so this sample was 2 centimeters in diameter. So I think it was something like 20 millimeters. So it's 20 microns resolution. You saw earlier that the fracture starts out at something like 12 microns. And so 1 pixel in the CAT scan is actually bigger than the fracture itself. And so all you can pick up in CTing it is a trace, which you can see here. This happened to be a chip within the sample where it was broken, which gives this big hole. But most of the sample that was flowing, this wasn't continuous, or it wasn't contiguous all the way along the sample. It was just on a small length of the sample. So we tried to get information on porosity changes, but if you're net dissolving 1 or 2 or 3 microns from a 12 micron aperture fracture, which you can't see in the first place anyway, you're not going to be able to pick up really many changes. So these are the contours of the sample, but it's not really very, which were easiest to see on the open fracture, but were not very useful. You can thin section the sample after you do it. You see some evidence of dissolution due to free face dissolution. You see contacting asperity pits. So this was a sample that was infilled with resin to be able to preserve the sample and then sliced. And this is a thin section slice across the fracture. These are the conduits of the fracture going into the page. This is infilled with epoxy right here. And you can see these asperities keeping it open. It's kind of a nice capillary model if you think about it. A stream tube here, a stream tube here, and a whole bunch of stream tubes here going into the page. And trying to understand the mechanisms. So I won't belabor this, we've already kind of explained it. So the idea is that where you see this in porous reservoirs as well as fractures, and that is that when the grains contact each other, these become preferential sites for dissolution because this has to carry all of this load. This is a bad figure, this is air. So all of this stress here can only be carried on this connection. And so the stresses by just the tributary areas have to be high on this region here and 0 on this region here. So as a result of that, this patch here will preferentially dissolve, and the mechanism by which it dissolves is you get a thin monolayer of water as a solvent on this interface, and the stuff that preferentially dissolves here much faster than the pore gets transported by a concentration gradient. So if you look at concentration versus length, then the concentration gradient looks like this. High here because it's dissolving at the same rate along here, but at the central part it has further to go than it does at the edges. So Fick's law suggests that for this axisymmetric case, this would be like a poker chip in plan view. The concentration is largest at the center, and it moves by diffusion by Fick's law. The flux is equal to diffusion coefficient times times dc dx. dc dr, I guess, in this case. This would be r. And so that's the mechanism by which it moves. And so the linkage with a fracture is that these Capri models can be applied to a fracture. This here would be the pore. This here is a pore, a pore, a pore, separated by intervening asperities. And this just happens to be a convenient geometry to be able to look at a single spherical contact with a space around it. And so exactly in this case, if it was a rigid material and it net dissolves stuff at the asperities, it would actually become more permeable, right? If you net dissolve material here and it's a rigid medium, so the stippled gray area doesn't change, as you dissolve material here, it will increase the porosity and the permeability will go up. The issue with a fracture is that it has a stress acting on it. So as soon as you dissolve material here, the upper fracture will follow with it and it will close. And so it's this overall difference between the top and bottom of these parts of the fracture which will close as it grows together. So it needs the influence of stress to drive that behavior. And of course in our sample we have a constant stress applied on the edges of the sample in the core holder. And of course in a reservoir you'd also have those stresses acting in the system. So you have a model that looks basically at this behavior, solving a diffusion equation to transport dissolved matter as it's dissolved into the contacting fracture. It goes into the fluid of the pore space, it raises the concentration in the pore, and all of a sudden at that concentration it's supersaturated. It can't hold that saturation in water. It's supersaturated because it's oversaturated by the fact that it's driven by the stress. And since it can't be held in solution, it will precipitate. So not only do you lose porosity by the fact that the grains are growing into each other and the volume in this region here is decreasing, you're also precipitating to actually eat up even more of this volume. So by both agents you lose porosity. So you can think about dissolution on the interface, its transport along that interface, and then once it gets into the pore, you can define the fact that the equilibrium concentration and the overconcentration dissolved in pore, overconcentration because it's come out from dissolution by stress, means that it will precipitate. And the rate at which it precipitates, as armoring, if you like, on the side of this pore, is controlled by this difference in the concentration of as it comes out and the equilibrium concentration that the pore can ultimately hold. And so you can make a little model that looks at dissolution, transport into the pore, and then precipitation onto the solid walls of the pore, just as this. And if you do that, you can model this behavior. This happens to be some data from an experiment that was just a whole bunch of glass beads, quartz, put in a reactor, and then put in a reactor under 70 MPa, and left with water in that reactor for the best part of a year, half a year, and to measure the porosity change as the load on that sample is constant, but as it's allowed to compact, as pressure solution allows the grains to grow into each other by this process. So as a function of that, the measured data are these dots here, the model are these symbols which represent these processes just as a very simple model. So you're able to follow exactly what you see here, is that you lose porosity in your bead pack as a function of time. Constant stress, so stress isn't changing. All that's happened is you've jacked up the temperature to allow this process to activate, and it slowly activates. It slows down. You could imagine that it slows down because this length here grows from being a very small number to being a large number. As this diffusion length gets longer, we know that for heat transport or for any diffusive transport, we have a dimensionless coefficient, which is a diffusivity multiplied by a time divided by length squared. So as this length doubles, then this time for any given dimensionless time for progress will quadruple. So as the diffusion length increases, the rate at which mass can be transported is reduced according to this square relationship here. And this just represents measurements of the concentration. Concentration before the stress is applied, zero stress. The stress is applied at this point here. Then you'd expect that if the solubility of this increases as the stress is applied, the concentration here will also increase. And this is what concentration will be measured if you sample from it. So as you apply a stress, you measure a change in concentration in the pore fluid. And that pore fluid is trying to also get rid of that by precipitate it onto the pore walls, but it can't do it fast enough, and that's why it stays up high. And as soon as you take off the stress at the end of it, you reduce it down to background. And this must be a re-application of stress after it. So you can do something like that in a fracture. Here you can represent the individual asperity contacts as these individual grains, and you can look at the growth of them. You can model the fractures as two halves. You can look at flow within these two halves from upstream to downstream. And you can just look at a mass balance of water being carried within the fracture, dissolving material from around these asperities in the free face, having mass ejected into the water by pressure solution from mass balance and being transported downstream, and then being able to precipitate, and then look at the growth in the contact area of the fracture. Contact area is shown dark here, growing as a function of time. And you can try and represent the data that we just looked at: changing temperature, changing temperature, changing temperature, changing temperature. Those are the experimental data that we have, and trying to represent that behavior by essentially by pressure solution in this particular case. And so the utility of that is that if you have a model that represents behavior, you can use that model to do what ifs. What's going to happen if I change the temperature 10 degrees, 100 degrees higher? What if I increase the stress? So these are just runs of a model to be able to look at what ifs. And so this is a model to look at the progress of permeability or aperture. So decreasing aperture would be decreasing permeability. What happens if we stress up a fracture to some magnitude and then we start increasing the temperature? If the temperature is low, you get a slow change in permeability. If you increase it, it becomes faster. And if you increase it again, it becomes even faster. This is in terms of days. This would be 1 year, etc. This would be 8 years or so, something like that, 7 years. So as you increase temperature, you increase the activation of this, and it becomes much faster. And you can determine how much faster it becomes in a quantified way. Likewise, you could hold constant the temperatures, but change stresses. And if you do that, as you increase the stresses, then you see that the rates increase a bit, not as quickly as they did before, just a small change. But as a result of changing these stresses, the closure that you get becomes larger with increasing stresses. So you don't change the rate at which it occurs very much as you change temperature, but you do change the end magnitude of the closure of the fracture. And so you can use that in a model to represent the behavior in a reservoir, which was part of the reason for this. Actually, the work was funded by as a geothermal project. So the final one, we'll just finish with this, was to do the same kind of experiment but on a limestone fracture. So this has much greater reactivity, much greater dissolution characteristics. It was done at ambient temperature, no temperature effects here. And it was flowed with groundwater, with dissolved components in it. It was in equilibrium with the rock. And then it was flushed with distilled water. So when it's flowed with groundwater, you see that the actual change in permeability, hydraulic aperture if you like, decreases by net dissolution from the fracture into the water, and then the closure of the fracture due to the action of pressure solution. But when you start injecting distilled water, all of a sudden you increase the rate at which you dissolve material, presumably by pressure solution, but then all of a sudden spontaneously the permeability starts going up again. And so we explained this as at the idea that you have a fracture that has these capillary flow tubes with fluid flowing into the page. As you net dissolve it, the walls of the fracture grow together and the permeability of this decrease. But once you get to a certain closure, then the rate at which pressure solution can transport dissolved components on a longer anvil. So you remember the contact goes from a short contact to a very long contact. As it gets longer, the efficiency of ejecting mass into the pore fluid decreases, and at that stage, free face dissolution on this conduit starts to grow. And as a result, if this grows and this pressure solution is swamped by this behavior, all of a sudden you get a wormhole developing its way all the way through from upstream to downstream. And that's exactly what it was. You get a single conduit down the middle of the sample as quite literally a wormhole, and that, of course, the ramifications for this for a geothermal reservoir would be that you'd have great flow through the sample, you'd have a great equation for mass rate of flow through the system because the permeability's gone way up, but you have almost no heat transfer area, and so this would go way down. And so the net effect in terms of the kinds of things we're talking about in this class would be that would be the behavior. And again, attempting to model that and trying to do things. And I won't go through that. Oh, so the other thing. And so trying to build constraint on this. This was a CT image of this and versus prediction. But the one thing that we did do was that I mentioned before that we tried to get an extra constraint on the experiment by impregnating the sample with epoxy and thin sectioning it. So if you inject epoxy resin into the sample, it only takes it in the fracture, and then you take the core and you just slice it literally across it, and then you can make a thin section that you can view under a microscope. The other thing that you could do to the sample is instead of injecting epoxy, you could inject something that you could make into a cast that wouldn't bond very well with the rock. And so one such thing is Wood's metal. Wood's metal is an alloy which might melt at 80 degrees centigrade and become liquid, and you can force it into the sample. And then once you bring the temperature down to 20 degrees centigrade at lab temperature, then you can make a cast out of it. So you can pull out of it a cast, separate the sample. You have this cast which represents the architecture, if you like, of the porosity, and then you can CAT scan it, or you could use a profilometer to measure the thickness and to get a picture exactly of that. And so you can use something like that to be able to check whether the results from your numerical modeling, where you have constraint on it by measuring flow rates upstream and downstream to get permeability distribution, mass balances upstream and downstream to get the dissolved mass, CAT scan, which doesn't work, but measurements of the aperture as gathered within a cast, if you like, an internal cast, a depth mask of sorts out of the system. And so that's just mainly to be able to reinforce the ideas that in our systems, that equation that I just mentioned is all important, and that it really links together all of these multiple fields that we're interested in. And that is exactly why we're interested in understanding these two parameters. And so in the terms of the big picture, this is exactly what's going on. So we know something about the governing equations of those. We know something about the mechanisms which are occurring as a result of fluid and mass transport and heat flow. So now we have to say something about the characteristics of our reservoir, and so that we can make some predictions on what's going to happen in our reservoir if we do modeling, simple modeling or complex modeling with the models that we know that these respond to. And to do that, we need to characterize the reservoir to understand what the geology looks like, and we can do that by knowing the geological environment. We can do that by characterizing it geophysically from the surface or boreholes, and by drilling it and taking samples, and also running pump tests and injection recovery tests to measure the initial conditions within the reservoir. So that's what we'll talk about from now on.